Hello, in this video I'm going to be taking a look at the terminal velocity of a ball at any time. Okay, so to get started, let's set up a coordinate system. Okay, so we're just going to draw some axes, and we're going to take the y direction to be positive downwards, and you could take it negative, but choosing the positive, it's going to simplify the calculations, because if you choose this to be negative downwards, it's going to make it a little bit more complicated having to deal with all the minus signs that show up in your calculation. Okay, so this is going to be our positive sense of direction, and this will be our positive x. Okay, so if we're trying to find the terminal velocity of a ball being thrown, let's draw a Freebody diagram to identify the forces. And in this case, we're going to be looking at the case where the drag force is proportional to velocity squared, so that term's going to dominate. Okay, so we're going to get the drag force is going to be some constant times velocity squared, and that's going to be in what? It's going to be in the y direction, so we can put a little unit vector to indicate that. And what other forces there on our ball? There's the force of gravity, so there's going to be the weight, which is going to be mg, and we can take that into we're choosing down, so this is going to be our positive sense of direction. And the drag force is going to oppose motion, so this is going to pick up a minus right here. Okay. So here we have our weight right here, which is what? mg, and here's going to be our drag force. Okay. Okay, so let's look at the special case. If we didn't care about say if we just wanted the drag force, say if we just wanted to figure out what the terminal velocity is, that we don't care about the velocity at any time. Okay, so if we use Newton's second law of motion, we get the weight minus the drag force, dv squared equals what? Mass times acceleration. And what do we know about terminal velocity? This term is 0, so we set that equal to 0. Okay, so what do we get? We get this constant d times v squared equals mg. And if we solve for v squared, that'll allow us to get our terminal velocity. So we get v squared equals mg divided by this coefficient. So we get what? Velocity terminal equals what? The square root of mg divided by d. And here we get what? Plus or minus, but we're choosing what? As we stated here, we're choosing our direction of motion to be positive, so we're going to choose the positive square root. Okay, now it's going to be a little bit more complicated if we want to find the velocity at any time t, given the forces acting on our ball. Okay, so we can find the velocity at any time subject to those forces when we're not neglecting air drag. Let's set up an equation, and we're going to have to integrate to find the velocity as a function of time for any time t, right? So this was the special case, right, when we hit terminal velocity, but we can also find the velocity at any time, any general time t. Okay, so we're going to have to use Newton's second law. Okay, so in this case, what are we going to get? We get mg minus dv squared equals what? ma sub y. Okay, so this is our y component of acceleration. Okay, but we're going to rewrite this right here as dv dt. Okay, so we're going to want to get all the v's on one side and all the t's on the other side. So if we play around with this a little bit, we get what? M dv divided by mg minus dv squared equals dt. Okay. So now we got a separable differential equation. So now this becomes a math problem. Okay. So if we want to integrate this, the first thing we could do is we could change, since we're going to be integrating over v, we need to change our variable. So let's choose our dummy variable. We're going to put v, let's put it to v prime, and same here, we're going to do t, and we're just going to change that to t prime. Okay, so now let's see what we get. Okay, so just rewriting everything, let's see what we get. Okay, so we're going to get the integral, and we're going to integrate from 0 to any velocity we want. We're going to get m dv prime divided by mg minus dv prime squared equals the integral from 0 to t dt prime. Okay, now this part's easy to integrate. Okay, so let's see what we get. Okay, so this part's just going to be t right here. Okay, now this part's going to be a little bit trickier. Well, what can we do? You could look this up into an integral table, but you can also do a substitution. If you're clever, you can be able to integrate this. Okay, so what do we have here? We have basically our variable squared and the denominator. Okay, so we're going to try this substitution. Let's set this v prime equal the square root of mg d equals hyperbolic tangent alpha. Okay, and what we saw here before, this term right here is what? This was our terminal velocity. So we could simplify this a little bit. So we're going to get our velocity terminal equals the hyperbolic tangent of alpha. Okay, but okay, we can hold off on this. We'll just mainly go to focus on this right now. But this is what this basically is. Okay, so if we figure out our differential, we get what? dv prime equals the square root of mg over d, which is our terminal velocity term, and the derivative of hyperbolic tangent is hyperbolic secant squared alpha. Okay. Okay, so let's see what we get. Okay, and let's also take a look at what our limits of integration are going to be with this substitution. Okay. So let's look here. So basically, what do we have? We're going to see how our variables are related. So we have the hyperbolic tangent function of alpha is equal to what? Here we got v prime over what? Terminal velocity. Okay, now if we want to see what this alpha is going to be, we're going to have to take the hyperbolic tangent of both sides. So we're going to get alpha equals hyperbolic tangent of v over our terminal velocity. Okay, and we can look this up when we see that our hyperbolic tangent inverse function is just 1/2 natural log of 1 plus x over 1 minus x, but in this case we're using alpha, so let's be consistent. Okay, so let's go ahead and substitute this stuff in and see what we get. Okay, so with our new limits of integration, we're going to get, okay, so let's see, on the right hand integral that involves the v prime, Okay, so our lower limit of integration is going to turn out to be 0, because when we substitute this in right here, the 0, what do we get? We get the hyperbolic tangent inverse, and that turns out to be 0 right here. And the upper limit's going to be a little bit more complicated, so let's just simplify right now. We're just going to put alpha sub u to let us know that this is our upper limit of integration. Okay, so let's just substitute in what we have so far. So we got m, and then we got this terminal velocity right here, term. And we get hyperbolic secant squared alpha d alpha. And we have all this over mg minus d. And we got this now, because this is squared, the square root goes away. We get mg over d times the hyperbolic tangent square root of alpha. Okay, so now you can see why we put this in our substitution. We had the square root of mg over d, all this squared. I mean all this under the square root, because this is going to allow us to integrate this, and we're going to get some cancellations. So the d squared, the d's cancel. So now what do we get? Okay, and so when we see here, this term has an mg and this term has an mg, so we can factor that out. So let's see what we get. Okay, so here we get our lower limit of integration, and right here, well, let's just go ahead and figure out what this is going to be real quick. So our upper limit, we're going to look at when v prime equals v. So we're going to see that our upper limit is going to be the hyperbolic tangent of v over our terminal velocity. So that's just going to be hyperbolic tangent inverse, of v over vt, which is our terminal velocity. So now we get hyperbolic secant squared of alpha d alpha over mg factored out, and we have this multiplying 1 minus the hyperbolic tangent squared of alpha. Okay, and if you can look this up in the hyperbolic trig identities, but here we have secant squared alpha, and this right here is equal to secant squared alpha, so these two end up canceling out, so that's nice. So let's see what we get now that we simplify things a bit. So now we have, and of course all this is equal to time. Okay, so let's see what we get. So here we got our terminal velocity over g. We just take that out and of the integral sign, and we get 0, and we get our upper limit of integration, which is our tangent inverse of v over terminal velocity, and now we just got d alpha equals our time. Okay, so now this has become easy to integrate. So let's see what we get. So now we get we have velocity terminal over gravity times alpha, and we're going to evaluate that at our upper limit of integration, which is the tangent inverse of v over our terminal velocity, and our lower limit of integration is going to be 0, and this is going to be equal to our time. Okay, so now when we substitute that in, we're going to get our velocity terminal over gravity times the hyperbolic tangent inverse of v over vt, and that's going to equal to our time, and we're almost there. Okay, so what can we do next? Okay, So we can get this term alone, so let's see what we get. So we're going to get the hyperbolic tangent inverse of velocity over vt is going to be equal to gravity times time divided by our velocity terminal. And if we take the hyperbolic tangent of both sides, we're going to get velocity over terminal velocity equals the hyperbolic tangent of gt over velocity terminal. Okay, so now all we have to do is just multiply through by this velocity terminal, and we've calculated our velocity at any time t, given that we can no longer neglect our drag force. And in this case, the drag force, it's a square term that's dominating. Okay, so now we see that we can calculate the velocity of a ball at any time t, and that's going to equal our velocity terminal times the hyperbolic tangent of gt over velocity terminal. And let's see if this equation makes sense. Okay, well, what's going to happen when time gets large? Well, we should expect that this is going to approach terminal velocity. So where do we have the time term in here? We have it in here. Okay, so how does if we think about it, how does the hyperbolic tangent graph look like? Well, basically it looks something like this. This is 1, and here's -1. And it asymptotically approaches -1, and it goes up here, and it asymptotically approaches 1. So when this term gets large, this term's going to approach 1. And what do we have here at the other term? We're basically going to have velocity terminal times 1. So the velocity it's going to basically equal velocity terminal as t approaches infinity, which just means as t gets large. And here we have what we desired, to find the terminal velocity at any time t.